So I hope everyone is fine. How was your Diwali?
It was okay, sir.
Okay. So this time I think there is like very less firecrackers, right? Okay. So after the last class, do you have any doubt, anyone? So there is no doubt after the last class. So how was your class test? Please respond. Then only I'll be able to know, no?
It was average, sir. It was average, sir.
What about others?
It's average,
Yes,
sir.
sir. Great, sir.
So was there any confusion with respect to the questions and all? So before starting the next topic, okay, we'll discuss the question paper first. Okay, we'll see what are the answers and all. Okay, is that okay?
Okay, sir.
Okay. Okay, so the first question was you have to explain the construction and working of either Geneva wheel or any other type of intermittent motion mechanism. Okay, so I believe intermittent motion mechanism, all of you understand. What's that? What does it do? So basically from continuous motion to intermittent motion, it gives us. Okay, so I believe most of you will be writing about I think Geneva wheel only. Okay, so this one is there any confusion with respect to this? How we construct and how it works? So that plate, that pin, okay, that grooved wheel, etc. Those things are there.
Hello?
ইন্টাৰনেট গৈছে নেকি? Okay, so I think I am back online. Is my screen visible now?
Yes, yes,
Yes,
sir.
sir.
Okay. So we are discussing that you have to explain the construction and working of Geneva wheel or any other kind of intermittent motion mechanism. So here I believe there should not be any confusion. All of you might have written about Geneva wheel.
Yes, sir.
Okay. So there the diagram also is important. Okay. So diagram is and next question is about like you have to analyze whether the following assemblies of links and pairs they are forming kinematic chain or not. Okay. So that is one close connection of three links with hinges and second one is close connection of four links with hinges. So three connection with hinges. So for that we already had two equation for lower pairs, right? So if you just like L for three connection with hinges, what will be the L, what will be the P link, how many joints, how many pairs? Three only. Link also is L also three. Then J also is three, right? Was there any kinematic chain here? Hello, am I audible? I hope I am
Yes, sir.
audible. Okay, so out of these two, is there any kinematic chain? I think the second one will come as a dynamic chain. Okay. So next question was like one small problem
Yes,
was
sir.
there with
Second one.
respect. Yeah. In the next question, there is a small problem with respect to your steering gear mechanism, right? Okay. So there you just have to find out that what is the suppose all those track arm length, okay, base length, okay, those things are given, and like you need to used in to find out the angle turned through by the outer wheel if the angle turned by the inner wheel was also given. So just you just have to use that particular law of correct steering. Okay, so that correct steering gear formula that you need to use, and other parameter whichever is not given, okay, that you need to find out. Next question is with respect to hooks joint, okay, or universal joint. So I believe all of you have tried this. Why we use universal joint? Anyone? The fluctuation of speed that was given, okay, so just have to need to you just need to use that given formulas, okay. So given today just find out like universal that including angle is given 20 degree, okay, unlike driving up speed was given, okay, and driven up there's some loading was there 9 kilowatt steady load, okay, and for that you need to find out the radius of gyration of the flywheel after driven up whose mass is already given, and the torque variation is given, maximum is 20%. That is there. Just you just 20% variation is have to consider, and just from this I equal to mk square, that also you'll be able to use. That m is already given, k you need to find out. Also that steady loading is given. Okay, so just use this given formula and I'll put down in that particular known formula. So that should give you the answer because that variation also is just found out. Okay, alpha is given 20 degree. Next one is with respect to finding out the degree of freedom problem. So what are the different steps involved for finding out degree of freedom of a given mechanism? So there are two
We have to
linkages
identify
given.
the kinematic pair, sir.
Yeah, first find out whether kinetic pair or not. Okay, then early kinematic linkages are definitely given. After that, you need to find out like properly you have to number the different links and show them. Okay, you just need to find draw this configuration diagram, and these are fixed link number one. Okay, so then correspondingly you just keep on giving the numbers to different links. Here basically this is also working like your guide here. Okay, this is this particular slider can be separated here. This is the slider, this is another slider that is there. Okay, this is on slider. So and what about this? Is it a is are there three different links or a single link? This one, is it a single link or three different links?
Three different seems to be.
No, this hex part is one single link, not three different links. Similar is the case here. Okay, these are all single links. This is suppose link number one, two. This whole thing is three. So 5. Then you keep on numbering them. Okay, say 7, 3, like this. Okay, so here in this case these are all different single. Okay, understood. So after that, you just have to find out n is given. Okay, from there try to find out the type of soil internal. From there we find out p1 and p2, and p2 then in this cases p2 higher pair is not there, so then most of both the cases will be 0. Okay, that if there is any redundant degree of freedom, that also you just find out. Here it is not there. Then after that, like effective degree of freedom, minus 2 p1 minus p2. Okay, and if that is redundant degree of freedom, which is not there, so this 3, and put those values and get the answer. Okay, and after that, this is the main question, that is you have to draw the cam profile for a roller reciprocating type of follower. Lift is given, radius of the roller is given, cam raises the follower with what kind of motion that is given. SHM profile you have to draw for 150 degree of the rotation, that is theta a equal to how much? Ascent stroke angle. Cam raises the follower means what? This is the ascent stroke angle. Okay, and it is with SHM. And followed by a period of 12, this is the first dual is given. Okay, so next follower distance for the next 100 degree rotation with uniform velocity. Okay, so theta d is given as 100 degree, but the difference is different type of scheme of movement is there. Uniform. Okay, don't mind my handwriting. Uniform velocity. Okay, and there is another dual. Let's find out. You'll be able to find out delta 2 at 360 degree minus these angles. Okay, addition of these angles, and n is given. Okay, and smallest radius is given. So there will be two basic stages involved. One is drawing the displacement diagram. Okay, and proper scale, etc. That is very important. Displacement diagram you have to draw first, then the cam profile. Okay. Next one is cam profile, and while drawing the cam profile, you just have to show about the kinematic inversion consideration. Okay, so this was basically about this whole question. So I hope you people have drawn this cam profile. All of you have drawn, no? So this one was for roller reciprocating type of follower. Roller follower means the center of the roller also, like that whatever is the radius of the roller, that also you have to consider. And while drawing that particular cam profile in the second case, that means, okay, so that radius value that you have to consider will become the minimum radius plus the roller radius. Okay, so that must you have to consider properly, and the rest is simple. So SN stroke you have to divide in draw like the SHM, what the way you have to draw for SHM. Next one is the uniform velocity, that straight line only will be there. Okay, and corresponding to whatever division you make in that dispersion diagram, from there we need to draw that particular cam profile. Is that okay? Any confusion?
No.
What about others? Okay, so if everything is okay, so we'll be going for another question then. Okay, so today we are going to solve we are going to draw another cam profile only, but this time this will be for a different type of. So previously we have drawn for roller follower, then we have also drawn for knife edge type of follower. So today we'll see for flat face follower or mushroom type of follower how to draw that particular cam profile. And in that particular case, previously already we have drawn about like inline case. Okay, so inline or radial. So that we already know how to draw for that case, and also we have studied for your offset type. Okay, So now out of these two, then the normal case is the radial or inline type. Okay, and if nothing is being specified, no offset distance, etc., that is given in the question, then automatically you understand that that is for radial type. Okay, so now we'll go through the question. Okay, so it's given that a flat face mushroom follower is operated by a uniformly rotating cam. The follower is raised through a distance of 25 mm in 120-degree rotation of the cam. That means raised through a distance of this means, so this is the right stroke and this much is the lift 25 mm. That is h equal to 25 mm. And for how long? For 120-degree rotation of the cam. That means theta equal to, that is ascent stroke angle equal to 120 degree. Then it remains at rest for the next 30 degree. Okay, and is lowered during further 120 degree rotation of the cam. That means now after that it remains at rest means what? Rest means ultimately if the follower is not moving or if it is remaining at rest, that is that we are talking about a dual stroke. So del one is this particular 30 degree and after that it is lowered. Lowered means the return stroke we are talking about. Okay, the theta d is once again 120 degree. Okay, now automatically you will be able to find out what will be the second dual, that is 360 degree minus this addition of this three. Okay, so 360 degree minus addition of this whole angle will give us 90 degree. Okay, so this is about the leaf value that is given 25 mm and the four angles. Next, the rising of the follower, it takes place with cycloidal motion. So this is once again important. So this theta with is which motion? Cycloidal. Okay, so you just mention it so that later on you don't forget or you don't make any confusion or mistake while drawing the ascent stroke. So ascent stroke has to be drawn in the for cycloidal profile. Okay, and the lowering which uniform acceleration and deceleration. So this is with uniform acceleration and retardation. Okay, so this is not a standard abbreviation for that, so you should not use it. Okay, just right now I am just for the sake of explaining I am using like uniform acceleration and retardation UAR. Okay, so now after that it is given that however the uniform acceleration is two-thirds of the uniform deceleration. Previously what happened, if you can recall, so we have talked about normal uniform acceleration and retardation where if this is suppose is the, let's consider this is the whole return stroke or ascent stroke, whole stroke, any one stroke you consider. And so it was 50% of the stroke was with uniform acceleration, 50% of the stroke was with uniform retardation. It was something like that if nothing is being specified. Now in that case, in this question it is being said that however the uniform acceleration is two-thirds of the uniform deceleration. Okay, so there is a relationship between them. That means throughout that particular stroke, it is not 50% and 50%, something like that. Okay, but uniform acceleration is two-thirds of the uniform deceleration. Okay, and next, this is sense that is happening. So you need to draw the cam profile and you have to find out the various values of the maximum velocity and maximum acceleration during rising, as well as maximum velocity and uniform acceleration and deceleration during lowering of the stroke. So first thing is you need to draw that profile and need to find out some numerical values for it. So I hope there is no all of you have understood the question and what are the changes that is there. Yes, let me know. Respond, please respond. Some of you should respond. If no one responds, then I will not understand anything. Depends whether you have understood or not. And you are repeatedly requested to draw these diagrams alongside me. Otherwise, later on you may find confusing. Okay. Okay, so now here we have seen that basically during even the lowering, that is the return stroke is with uniform acceleration and retardation, but during the return stroke what is happening? The uniform acceleration is two-thirds of the uniform deceleration. So in other words, we can say uniform deceleration is 3 by 2 of the uniform acceleration, right? So if we consider the uniform acceleration value to be f, then we can write the uniform deceleration to be, because it is already 2, 3 of f. Understood? We can write like that. Okay. Now we'll find out the time of acceleration. So we know this is for relation for linear velocity, so f v equal to u plus at, that we already know. Okay, so now the final velocity, if we are talking about, that is v. Okay, so it has started from what? Zero velocity, that is the initial velocity is zero. This is zero, so what will remain? V equal to ft, or we can write t equal to v by f. This is the first case. This is how acceleration, the linear velocity, and the time is related for acceleration. Now we are talking about return stroke only. Okay. Now time of deceleration. Now what happens? Initial case in that whole stroke, that is the return stroke. Some portion is with uniform acceleration. Some portion is with uniform retardation. Okay. So now the time of acceleration we have found out as this. Okay. We need to find out the time of deceleration. Now what happens in that case? Whatever is the final velocity in the case of acceleration, that becomes the initial velocity for the next case. Okay, next half, that is the deceleration case. So initial velocity will be v, and after deceleration it has decelerated or retarded up to zero, or final velocity is zero. So once again, by using v equal to u plus at, we can write that is the final velocity equal to zero. Initial velocity now is v, and this is we are talking about the deceleration or retardation. Okay, so t, we can write this is the uniform deceleration value. Okay, we can write 3 by 2 f this much, and t is t dash. Okay, so t dash we are considering as the time of deceleration, and this negative side is because we are talking about deceleration value. Okay, already you have obtained how they are related, that is 3 by 2 whole into f. So this much we have written 3 by 2 into f. Okay, so from here we can write t dash to be 2 by 3 of t. Okay, so we have used for p by f, this is nothing but t, already have obtained. Okay, so t dash equal to 2 by 3 t. So what I can write, that means this is the time of deceleration, and this is the time of acceleration. This is the time of acceleration. Okay, or time of acceleration. So I can say so the time for deceleration is two-third of this, two-third of the time of acceleration. Okay, up to this much I hope it's clear, the relationship. Why we are finding out? Because we need to first draw the displacement diagram properly, and how much is the while drawing the displacement diagram. So there will be two strokes, ascent as well as descent. For ascent stroke there is no problem. For the descent stroke some differences are there, like it was not 50% which has a high uniform acceleration, and other 50%, remaining 50% is uniform deceleration, but there is certain relationship, and that particular thing we are going to find out. Okay, so that's why you are doing this. Okay, how much time it is taking, how much or displacement that is there.
Okay,
Okay,
sir.
okay. So now regarding displacement, so now there is two strokes, and again within that particular stroke there is acceleration portion, there is deceleration portion, right? So now during the portion of acceleration, so all of you already know as equal to ut plus half at square, that equation for displacement. Okay, for deceleration we can once again use this as equal to ut plus half at square. Okay, so and from there we can obtain that. Okay, ut equals to p equal to ft. Okay, so yes or no? v equal to ft. So this ft, because we already know now the initial velocity itself is v, and v is equal to ft. So this ft whole into this time is already we have obtained 2 by 3 of this t, okay, because that becomes t dash, right? For deceleration, that is time is t dash, no? Okay, t dash equal to 2 by 3 of t. Similarly, for other portion, other velocity, we are just putting that, okay, and that is the initial velocity is v equal to ft, and time taken is 2 by 3 of t. After simplification, what we have obtained? So this is equal to 2 by 3 of half of ft square, and now this half ft square already we have. This is half ft square, right? Half ft square is the displacement during the acceleration phase, and for deceleration phase it is 2 by 3 of half ft square. Okay, that means what we can say if we compare these two. So the distance traveled during deceleration period is 2/3 of the distance traveled during acceleration. Okay, so now we have found out the relationship between with respect to the distance, okay, that is being traveled during the acceleration portion of the return stroke and during the deceleration portion of the return stroke, because the return stroke itself is comprising of two different portion, two phases, that is the acceleration phase is there as well as deceleration phase. Up to this much I hope that's clear. Yes. Okay, so now we are ready with that. We are equipped with the values of displacement during that particular return stroke. Okay, with respect to the initial rise stroke, we don't have any problem. We know that throughout the rise stroke, that is the cycloidal motion profile that is there. Okay, so now we are going to draw the displacement diagram. For that, we are going to consider a proper scale for that. Okay, along x-axis, whatever is your uh, whatever is the scale that you consider, and along y-axis will be considering the proper scale. Okay, so we know along x-axis this is the angular displacement, okay, or ultimately in terms of time also you can say, okay, so theta, or ultimately in terms of time also you can say, and along y-axis this is the displacement, okay, or lift you can say, displacement of follower or the lift. Okay, so now what is the relationship that we have obtained? So now once again, just like in the previous cases, so many times we have been drawing this displacement diagram. So well, this as per scale we have to consider success. Okay, here we'll be dividing as per the whatever scale, that theta a, then the first 12, then theta d. Okay, and now this is about right stroke. This much is your dual, first dual. This is return. So right stroke is with cycloidal motion. Okay. So cycloidal motion profile we'll use. Okay. Already we have discussed. Okay. How to go for cycloidal motion profile. So like taking that particular leaf flow and all. Okay. Taking the proper radius for this particular circle. If you have forgotten, just go through the displacement diagram profile, okay, for cycloidal motion. So just in this case, just take the values, okay, and we'll end up getting the cycloidal motion profile here, okay, displacement profile here for the cycloidal motion. After that, for the dual, there is no problem. It will be like this. And now here, this is with uniform acceleration and retardation, but the case is previously we used to draw like exactly at the middle, okay, up to the first half, that is with uniform acceleration, second half with uniform retardation. Now we have obtained that the distance traveled during the deceleration period is 2/3 of the distance traveled during acceleration. Okay, so now what we can say, like ultimately we know that along the x-axis we can say we can consider the theta, or ultimately the time also. Okay, same thing, because it for because theta means angular displacement. So for a particular angular displacement to take place, it takes, whenever it is uniform motion we are talking about, then it takes a particular time. Okay, so in terms of time also we can discuss, no problem. So now what we can say, that means the time of acceleration is 3 by 5th of the total time of return, or ultimately in terms of displacement also we can say it is 3 by 5th of the total displacement. Okay, that is we are talking about the time of acceleration. So 5, you can think as if like the return stroke itself, in your mind you can consider like as if three divisions, five divisions equal space division you're making. Okay, and out of this five equal space division, previously it was like 50% was with uniform acceleration, another 50% is uniform retardation. Now 3% out of this 5% is, we are talking about uniform acceleration, and the rest 2%, 2 part out of total 5 part, that is the uniform deceleration. That means this particular vertical line will be the vertical line where we are going to make those equal space vertical division. Previously, we used to take the mid vertical line, and we used to make that particular division. Depending on suppose 6 division, if we have made on the total return stroke, then we'd be making 6 division here. Similar is the case here. We have make 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Total 10 division. So 10 vertical equal space vertical division in this particular line. Okay, will be making. So rest is simple. Rest is similar. The way we are going to draw it is similar. Okay. So for the first 6 division from this side will be joining. So first corresponding vertical line and corresponding this inclined line we'll have to consider, and wherever they meet, ultimately we are going to take that particular point. And after getting all those points, we'll draw that particular curve. Okay, smooth curve, and that will be the particular displacement diagram in that case. Understood? So this was the different case here. It was not 50% uniform acceleration and uniform retardation. It is not like that, but rather there is a certain relationship that was already given. Displacement diagram, I hope that's clear. Let me know.
Yes, sir.
Rishikesh,
Yes, sir.
Shankar,
Yes.
Nilupal.
Yes, sir.
Okay, so I hope for others also that is clear, and all of you are trying to draw alongside me, right?
Yes, sir.
Okay. Okay, so now the first part is over. That means how we have properly drawn the displacement diagram for this particular case. Next is we just have to draw that particular cam profile. Okay, and for drawing the cam profile, initially we need to have that particular circle. Okay, so in that case, the base circle value is already given. That is the minimum circle radius is already given, and this is what type of follower. Right now this is a flat face matter follower only. Okay, we are not talking about any roller follower and all, and that's why directly the contact point or the trace point will be directly at the face of the follower itself. So we don't have to consider the that additional roller radius for finding out that, for drawing that particular your circle. Okay, so now this time what we'll consider, once again that kinematic inversion will be there. That means the will assume as if the cam is stationary and the follower is rotating around the cam. That assumption is just write down. Okay, assumption is just write down. That can also face 1 mark. Okay, proper assumption you write down, and after that first step is we need to consider the, by considering that RC value, we are going to draw this particular circle. Okay, this circle will complete it. So where O is the center of that particular circle. Okay, so and other things like as nothing is being specified here, so we'll just consider like it is a inline or radial type of cam and follower arrangement. Okay, and we always start with the vertical portion. Okay, initial vertical position we consider as the initial position. So that means first position of that particular follower is if it is here. Okay, should not, you should not consider somewhere here or here as the first position. Okay, we always consider like this the particular, that is the standard way of doing. So now if this is the vertical axis of the particular your follower, okay, that's a reciprocating type only. So now what we are going to do, depending on whatever is the angles mean that f and stroke angle theta a and the dual and theta d etc, whatever is given. So as per that we are going to make the division here also. Okay, so if you can recall, then how much was the value. So theta a was 120 degree, first dual 30 degree, then once again 120 degree. So this much division theta a delta and delta 1 and Okay, making the major division. Okay. So after that, what we need to do, depending on how many divisions you have made in that correspond your previous displacement diagram. Okay, so we have in this case we have made 8 division in the ascent stroke and 10 divisions in the descent stroke. For the uh, dual, there should not be any division. No need for any divisions now. Okay, so correspondingly, this particular 120 degree, the whole angle, we are going to divide it into equal number of event space division that we have as that we have done in that particular acceleration this displacement diagram. Okay, so we have made 8 divisions, so this 120 degree also divided 120 degree divided by the 8. Okay, so whatever you get as per that, taking the protector, you just give the division. Okay, so first division, second division, like this we'll make all those 8 division. Okay, and don't forget to give the proper names here. Suppose one division names, okay, 3, 4, etc., etc., whatever you have utilized here in the displacement diagram. Same nomenclature you should use. Now after that, there is this particular dual. So during dual, you not no need to do any kind of division and all. Okay, so this is like this, and this descent stroke also, depending on how many divisions you have previously made in the your displacement diagram. Some say in the same division you are going to make this division here. Okay, so you're also like 9, 10, 11, 12, etc., etc. This way we are making up to 18. Okay, so this 10 division will make. Okay, so after that, once again, I hope that's clear.
Yes, sir.
Okay, thank you.
Yes.
Okay,
Yes, sir.
so
Yes, sir.
next thing is somewhat similar only. Okay, so now we'll go back to once again the displacement diagram, and we'll find out this 1 dash, 2 dash, 3 dash, 4 dash, 5 dash, 6 dash, etc. This displacement of the follower will measure using scale, and that much we are going to extend or reproduce here in this particular diagram. Okay, so suppose 1 dash will measure, and from first division we will extend this much up to 1 dash. Similarly, from 2 along this particular division only up to 2 dash, whatever is this particular distance, that much we are going to extend and give the name to this. Okay, similarly 3 dash, 4 dash, up to this, all those division will, all those these distances, corresponding distances from the displacement diagram will take, will measure, and that much we are going to extend it. Okay, up to those points, and don't forget to name those points. Similar is the case for the this end of the dual. Okay, at the end of the dual it is similar as that of the end of this particular your ascent stroke itself, because throughout the dual it is the same position, there is no movement of that particular follower, so same displacement will be there, so same extension. Okay, so after that, similarly, from that particular return stroke you have to measure this distance and this distance. Okay, like this. Okay, so this first distance you will measure, and correspondingly you will be extending through from that particular division, 9 9 days, 10 10 days, 11 in days, etc., etc., up to 18 that you will do. Okay, this is the next step. Done. Okay, so I hope that one up to this one is clear. So after that, we are left with the last portion. That is now what we will do. Now all these 1 days, 2 days, etc., etc., those points are nothing but we are talking about the follower point. Okay, so now we have to draw the follower in all the positions by how? We're by drawing perpendiculars to the radial lines at 1 dash, 2 dash, 3 dash, this extended line. Okay, so this is kind of the, we know this is a flat face mushroom follower. That means the contact surface is something like this. Contact surface of that particular follower with the cam is something like this. Okay, so now this particular portion only we are drawing. Okay, we are not going to draw the whole portion of that particular follower, but we are just going to show the contact portion. Okay, because we are interested in that. So if we know about this particular contact point throughout that around that.
ঋষিকেশ,
Ah,
ছাৰ এৰিলে দেখোন।
huh? এইটো এৰি দিল
ছাৰ
নেকি ছাৰে?
একো কোৱাও নাই দেখোন।
ৰেকৰ্ডিং চলি আছে দেখোন।
সেইটো জানো।
Hello.
ছাৰ য়েছ ছাৰ।
I think in between some network disturbance was there, no?
য়েছ ছাৰ।
Okay, just do it.
Yeah.
No, no, these days so many disturbance we are talking. So up to how much we have discussed? So division is done. After that, drawing that particular your that follower portion. That you have understood now. That must we have shown. Yes, drawing this. Network is disturbing. I think it's fluctuating. That's why in between it is going. Okay, so hello. Please respond. Then only I'll be able to understand whether I am
Yes, sir.
online or
Now
not.
audible, sir.
Yes,
Okay,
sir.
okay. Okay, so
Yes, sir.
the last portion. Okay, thank you, thank you. So the last portion, that is this particular drawing of this particular flat face follower. Okay, perpendicular to the extension line. This much we have shown. No? You have seen?
Yes.
Huh? Yes.
Yes, sir.
Okay. So after that, the last step is like through your freehand curve, you have to join this end portion of this particular your flat face follower portion. Okay, and it has to be tangential to that. Okay, so just like in the previous cases you have been doing like that. Okay, so join with a freehand smooth curve these points, okay, which has to be tangential to the end portion or end face of the particular follower. Okay, knife flat face type follower, and up to this much, that is this ascent stroke, there is no problem, you will be doing like that. And after that, during the descent the first duel, it has to be the constant radius curve. So considering this much as the radius, you just draw that. Okay, constant radius curve. And after that, once again, like with free hand, okay, you will be joining that up to the end of the descent stroke. And once again, at the descent stroke, this is the dual only. Okay, and dual. So this will be once again constant radius curve. Just darken it. And at the end, with a cursor, you show that this is the required cam profile. Okay, so that will be done. Understood? So this is how we draw the cam profile for this kind of follow. Okay, here the interesting point was this is a mushroom type of follower, and next thing was the return stroke. It was not like that means that we have seen that it is also possible that some of the like 50% of the previously 50% of the stroke was with uniform acceleration, rest 50 was with uniform deceleration. But in this question, we have seen that this condition may vary. Okay, it's not like a universal condition. Okay, so that's for today. So the next portion, that is finding out the like values. Okay, the of minimum velocity, acceleration, etc. I believe all of you will be able to do because that is numerical or numerical values only. But you should be careful while utilizing triangles and all. It has to be in radian. Okay, so those things you just remember. Okay, so with this we'll stop here for today. If you have any confusion, you can ask. In the meantime, I'll be taking the attendance. Nilukol,
Present, sir.
Chansar,
Present, sir.
Arsisman,
Present, sir.
Rehan,
Present, sir.
Partha, Partha. He is here, but he is not responding. Seems like absent-minded. Okay. Rishikesh,
Present, sir.
Permiki,
Present, sir.
Nahosal,
Present, sir.
Teza, Teza, absent. Rishikesh not,
Yes, sir.
and Emil, absent. Okay, so we'll stop here for today. If you have any question, you can ask. Otherwise, we'll stop.
No question, sir.
No question. Others? What about others?
No, sir.
Okay.
No, sir.
Then we'll end here.
Yes, sir.
So I urge all of you to try solving some problems on your own. Okay. First, you
Sir,
try
one
this.
thing, sir. Can you, sir?
Yes.
Sir, for solving numericals, we need a book, sir. Can you suggest one book, sir?
Yeah, I have on initially also I have suggested that you can take like Ratan book, okay, maybe VP Singh book, any theory of machine book you can take like for solving numericals only, na, that you need. Okay.
Yes,
Otherwise,
sir.
the concept is like Ghosh and Malik book is good. Ratan also is good. You can take Ratan book or Sadhu Singh book also is available. Okay. Whatever you get, hold on. So initially you try with that. Okay. And for
Okay.
reference, you can take like Ghosh Malik. That's good book. Okay.
Yes, sir.
Okay. Thank you.
Thank you,
For
sir.
active level, like Ratan book, VP Singh, Sadhu Singh, those are okay.
Okay, sir.
Okay.
Hands up.